I now have 5 exercises for you to practice kinematics equations. So what I'd like you to do is read the problem, turn off the video, try to solve the problem, turn the video back on. I will first start by giving the answer, then I will work it through in case you need help with that answer. Okay? So good luck. All right, hopefully you were successful in solving the problem, and the answer is 3.13 meters per second up. Okay? So let's go through over here and solve it. A boy can jump up as high as 0.5 meters. With what initial velocity must the boy leave the ground to reach the maximum height? So I'm going to draw my picture. Here's my boy. He's jumping up. Oh, we'll make him smile a little bit there. There you go. He's going to jump up, and he can only go high as 0.5 meters. So there's my picture, my axis up. At the very top here, he can't go any higher. The final velocity there is 0. There's my distance here. I want to know with what upward velocity, VI. I also am fortunate to know the acceleration of gravity. Anytime you're going vertically, you know what A is. That's acceleration of gravity. Okay? So we can write down an equation that we have that has all these things in it, and it's really the only one without time. VF squared equals VI squared plus 2AD. So we plug in 0, VI we're looking for, VI squared plus 2, negative 9.8 times 5. Oops, sorry, I'm squishing there. And when I bring that over, the negative signs will cancel. You will never take a square root of a negative number. VI then is 3.13 meters per second, and I know the direction is up, plus I got a positive answer. Okay, here we go, is problem 2. So read the problem, solve it, try your best, turn off the video while you're working on it, and then turn it back on for the answer. Okay, the answer for number 2. A we have is how high does it rise is 4.9 meters. And B, we have the initial velocity is 9.8 meters per second up. That is the direction the coin is tossed, excuse me. Okay, so let's look what we have here. I'm going to draw the picture here and then solve it on the side. So we have a coin. Here's my coin. And it's flipped up into the air, and then comes back down 2 seconds later into my hand. Okay? How high does it rise? So we want to know that. How high does it rise? And we also want to know the initial velocity of that coin toss. So we're looking for VI, and we're also looking for the D. Okay? Well, just like in the previous problem, we know that the initial, after the initial toss, the final velocity at its highest point is going to be 0, because then it's going to be on its way back down. Okay? So we also can find you might want to find, some kids find B, find the initial velocity might be even easier. So let's do that. Let's find B first. So we're going to do for B, we're going to go VF equals VI plus AT. My final velocity is a big fat 0. Initial velocity, that's what we're looking for. Acceleration. Oh, yeah, that's right. Vertical problem. Negative 9.8 meters per second squared. That is a plus sign. I apologize. Times time. Well, what would the time be? If it's 2 seconds to go up in here, it takes 1 second to go up and 1 second to go down, because gravity acts equally on the way up and on the way down. So notice I wrote the second here, but just to show you that this second will cancel with one of these. So you would be left with VI is 9.8 meters per second. And I know it's up because it's a positive number and we're tossing the coin up as well. Okay, now I'm going to go back to A. And why I decided to do that was because I can use the VI now in my equation, but I can also tell you this. We could also say that on the way back down, it fell the same distance that it rose. So the initial velocity on the way back down is 0 as it's going down. So we can use D equals VIT plus 1/2 AT squared. And I'm going to find out how far it fell, which would be the same as how high did it rise. So D equals, well, it's on the way back down, the VI is 0, so this whole thing is 0. We have 1/2 Negative 9.8 times 1 second squared. Half of 9.8 is 4.9. And notice it's negative here, but that's because it's going down the way I solved it. We know that though it rises a positive 4.9 meters. Now on to number 3. Okay, hopefully you were able to solve it. The answer is 37 meters per second. 37 meters per second. Let's see how we do that. Okay, we have a ball rolling at 4 meters per second. So we're going to have the ball here. It's rolling at 4 meters per second down a hill. So choo. Okay. We do know the initial velocity is 4. It is uniformly, so we know also the acceleration rate. It's given here. If you weren't sure if that is acceleration, the units can tell the story. The unit here is an acceleration unit. We know the time is 6 seconds, and we are looking for the ball's final velocity. So hopefully we have an equation that has all that in that, and we do. VF equals VI plus AT. So now we literally can just plug and chug. VI is 4 plus 5.5 times 6. Okay, left off the units, but they all would be fine together. And when I solve for my final velocity, I get a total of 37 meters per second. Okay, on to problem number 4. So read it, solve it, and then check back with the video. The answer is 17.14 meters per second. I'll write it right here, 17.14 meters per second. 17 would have been fine. Okay, let's go through and see how we solve that. A student drops a physics book, alas, who would do that? From a bridge 15 meters high. With what speed does the book strike the water? So we have a book here being dropped from a bridge into the water below. Well, that's not a very straight line, but we'll have to do. Okay, we know the distance is 15 meters. We know gravity. Acceleration of gravity is at work here because it's a vertical problem. And we are looking for the final velocity. Well, what's the initial velocity of a book dropped? Any object dropped from rest is 0 VI. Okay? We have one equation that really is the one to go to whenever you don't have time in it. VF squared, VI squared plus 2AD. VF squared equals VI squared, which is 0, to negative 9.8 and negative 15. Well, why did I put negative 15 there? Because the book is falling down. All our down, we're going to have direction of negative because D is really displacement in that equation. So we're going to put our sign in, do one multiplication out, and take the square root, and that's where I get 17 meters per second. Okay, our last problem, number 5, and it looks a little more involved. So let's do this together. It says a boy bikes a 2,000 meter race by uniformly accelerating over the first 75 meters and then biking at a constant speed over the remaining distance. The final speed reached is 35 meters per second. So let's draw out this picture. So here is my bike race, this big long race, here we go, where at the end here is the 2,000 meter finish line, yeehaw. And here is my start, okay? Well, this very first section, and I'll darken it, that's the 75 meters where the boy is accelerating. So that's my distance, 75 meters. What else do I know? I know my initial velocity. When you start a race, you have to start from rest, so that's 0. I also know that my final velocity, that's reached right after this point, is 35 meters per second. And that's the constant velocity used all the way throughout the rest here. So it's just accelerating at that very little bit. And we want to know that acceleration. We want to know what the acceleration is, and we want to know the time it took to do that. So to find acceleration, what we can do when we don't know time at all, that is our VF squared equation. So VF squared equals VI squared plus 2AD. Okay? We can plug everything in that we know because we know the final velocity 35. VI is 0. We know 2. A we're looking for, and D is 75. and my acceleration comes out to be 8.2 meters per second squared. So that is my acceleration for part A. For part B, what's the time? Well, the easiest equation when you want the time is the VF equals VI plus AT. I'm sorry, that's an equal sign. Final velocity we know is 35. Initial velocity is 0. Acceleration we just learned previously. So the time, 35 divided by 8.2, the time that we get for that is 4.3 seconds. Okay, now on to C. Find the average speed over the entire 2,000 meter race. And this can be a challenge. And you might say, well, average speed, that's not a challenge. Average speed's pretty easy. It's total distance over total time. And you're right. 2,000 meters is the total distance, but it's the time that we have to figure it out. We know 4.3 seconds is the initial time just for that 75 meter part. But we also have to figure out what the time is for this total distance here. So let's get that. Well, I'll do it up here for sake of ease. To find the time here, I can find using my average velocity as distance over time, or I can also write that differently. I can also write that if I cross multiply and solve for t, I can say that that time is distance over the average velocity. So if I take 2,000 meters minus 75, because it's not the entire 2,000, it's 2,000 minus 75, and I divide it by 35, I will get the time it took just for this distance from the 75 meter mark to 2,000. And when I do that, I get a, 55 seconds. That's what I get for that distance. So the 2,000 minus 75 is 1925, divided by 35 is 55 seconds. So I can come down to this equation, add 55 seconds here, add that, which is 59.3, put it into 2,000, and my average velocity for the entire trip, 37 meters per second. There you have it.